our third problem deals with the ideal gas equation. It says a 1 cubic meter tank containing air at 10 degrees Celsius and 350 kilopascals is connected through a valve to another tank containing 3 kilograms of air at 35 degrees Celsius and 150 kilopascals. Now the valve is opened and the entire system is allowed to reach thermal equilibrium with the surroundings, which are at 20 degrees Celsius. Determine the volume of the second tank and the final equilibrium pressure of the air. Okay, so I draw the schematic here already. Basically, we have these two rigid tanks. Both contain air, different volumes and mass of air. Here we're just gonna call this tank A and tank B. And so the first assumption that we have to make is that air behaves as an ideal gas. And so if we do that, we can just use the ideal gas equation to calculate the volume, which is the first thing that we need to compute here, the volume of the second tank. So if we do that, we can just write that the volume in tank B will equal the mass of the tank at the initial state. We're just looking at the initial states for now, like before the valve is opened, times the ideal gas constant times the temperature of the tank at the initial state, and divided by the pressure, the initial pressure. And all of this is for tank B. And so we have all of this. We just replace the mass is 3 kilograms, right? The constant, using the SI units, this is, you can find it in the textbook. It is 0.287 kilopascals, cubic meter, kilogram, Kelvin, right? And then times the initial temperature of the tank, which here we say is 35 Celsius. If we convert that to Kelvin, that turns out to be 308. Kelvin. And the pressure, the initial pressure is 150 kilopascals. Okay, so if you solve for this, you end up with the volume of tank B at the initial state being 1.768 cubic meters. So that's the first answer to this. We can also determine what's the mass of the first tank using the same approach. So we can say the mass of air contained in the tank A at the initial state will equal, using the ideal gas equation, to P1B RT1. All of this is for tank A, right? And so we just do the same. We just replace with the information that we have. The pressure initially is 350 kilopascals. Then the initial volume is 1 cubic meter. The constant and we multiply this by the initial temperature in the tank, which is the 10 degrees, which in Kelvin that will be 283 Kelvin, correct? And so if you solve for this, then the mass of air in the tank turned out to be 4.309 kilograms of air. So now we can just calculate the total volume and the total mass of the entire system, which will be for the volume, the total volume will be just the addition of volume A plus volume of tank B. And if you input the numbers, that will be 1 cubic meter plus 1.768 cubic meters. Okay, so that's the volume of the entire system. For the mass will be the same. The total mass will be the mass of tank A plus the mass of tank B. In this case, we determined the mass in tank A to be 4309 kilograms, and the mass of tank B is 3 kilograms. And if in that case, the total mass is 7.309 kilograms. Okay. It will be like the pressure at the final state will equal the mass of the of air in the system, the times the constant. In this case, we already wrote down what's the value in the SI system, and the temperature at the final state over the total volume of the system, which we also calculated. And so we just replace this. So the total mass was 7.309 kilograms for air. Then the constant again is 0.287 kilopascals cubic meter or kilogram Kelvin. And I don't have enough space, but let's see, let's try. The second temperature, it will be the temperature of the surroundings, right, which is 20 Celsius, which in Kelvin that will be 293, right, Kelvin. Don't think you can see that there, so I'm just gonna write it here. This is Kelvin, right, times this is the mass of the system, this is the constant, the ideal gas constant, and then the volume here, sorry, will be the total volume, which we calculated as 2.768 cubic meters. Okay, so when you compute all of that, your final answer should be 222 kilopascals. Yeah. And that is the end of this problem. And our last problem is a problem that deals with the compressibility factor. So it says carbon dioxide gas enters a pipe at 3 megapascals and 500 Kelvin at a rate of 2 kilograms per second. CO2 is cooled at constant pressure as it flows in the pipe, and the temperature of the CO2 drops to 450 Kelvin at the exit. Determine the volume flow rate and the density of carbon dioxide at the inlet and the volume flow rate at the exit of the pipe using first the ideal gas equation, B, the generalized compressibility chart, and then also determine the error involved in the first case. And so, okay, I already have the schematic of the situation here. There's a pipe, there's carbon dioxide flowing through the pipe, and it has the initial pressure, temperature conditions, and the mass flow rate. And then it's basically, as it flows through the pipe, the temperature goes down to 450 Kelvin. So the first thing we're going to do is just write down the properties for this problem here. And in this case, for CO2, we have the gas constant as 0.1889 kilopascals per cubic meter per kilogram Kelvin. You also want to write down the critical temperature for CO2, which you can also get from the charts in the book. It's 304.2 Kelvin. And the last property will be the pressure, the critical pressure, which in this case is 7.39 megapascals. Okay, so the part A just asks to determine volume flow rate and density of the carbon dioxide at the inlet, and the volume flow rate and exit at the exit of the pipe using the ideal gas equation. So let's see, I'm just gonna make sure that I don't write over the statements again, or the problem statement. So the first thing will be to calculate the volume flow rate using at the inlet of the pipe, using the ideal gas equation will be and so we just replace this with the information that we already have from the problem statement. We know that we have 2 kilograms per second. Then our constant for carbon dioxide gas is 0.1889. And the initial temperature at the inlet, is 500 Kelvin. Okay. And this over the initial pressure, which in our case is 3,000 kilopascals. Okay, if you compute that, it turns out that volume flow rate at the inlet will be 0.06297. And this should be okay. In kilopascals. So this will be cubic meters per second. All right. Then we do this the same. We go ahead and calculate the density of the carbon dioxide, and we can just do that by dividing the pressure of the inlet, of the gas at the inlet, dividing that by the ideal gas constant for CO2 and the temperature of the inlet, right? Using the ideal gas equation. So we basically have density, which is mass over volume. We replace this. So we have the initial pressure here was, we said 3,000 kilopascals, correct? And then our constant Kelvin. And then our temperature at the inlet, which was 500 Kelvin. And so that turns out to be 31.76. Okay. And then the problem also asks for the volume flow rate at the exit of the pipe. And so it will be the same if we use the ideal gas equation. We say that that the volume flow rate at the outlet should be equal to the mass flow rate of the gas times our ideal gas constant times the temperature at the outlet of the pipe, and divided by the pressure at the outlet. Okay, so we can just go ahead and replace this. Okay, the temperature at the outlet. And the pressure, which is 3,000 kilopascals. So the flow rate at the outlet will be 0.056667. And this will be again cubic meters per second. Okay, so these are the calculations using the ideal gas equation. Okay, so part B of this problem has to use the generalized compressibility chart to determine the same variables that we determine using the ideal gas equation. So for that, the engineering equation solvers uses a function for the compressibility factor. You can just look at the chart in the book. And basically what we'll do is just determine first what's the compressibility factors for the inlet conditions and then the outlet. And so for that we have the pressure here, this should equals P critical. And this is the reason we look for these properties at the beginning of the problem. Right, so in this case we have P1 is 3 megapascals, right? And the critical pressure will be here 7.39 megapascals. And so this is 0. Okay. Then we want to look at the temperature ratio here at the inlet conditions. So this should be equal T1 or T critical, which was 50 Kelvin, sorry, over 300. 4.2 Kelvin, and so this ratio will be 1.64. So using the chart and these two conditions, looking at these two factors, we get that C1 should be 0.9791. So that's the factor for the inlet conditions. Then we do the same for the outlet conditions. So I'm just gonna erase this. Okay, so the second pressure we have here again is 3 megapascals. This hasn't changed. Well, this was the same. And then this condition, the second temperature at the outlet drops to 450 Kelvin, and the critical temperature is 304.2 Kelvin. So again, this is 407, and this is sorry, this is 1.48. And so using these two ratios, we just look at the chart to determine what's the compressibility factor for the outlet conditions. And in this case, it will be 0.9656. Okay, so now we can go ahead and just calculate the volumetric flow rates at the inlet and outlet of the pipe, right? So it will be the compressibility at the inlet, the mass flow rate, T1, so if you input these values, you have the compressibility factor. This is 2. Well, you have the constant from here, and the pressure at the inlet, which is 3,000 kilopascals. These turn out to be 0.06165 cubic meters per second. And if you compare this result with the result that we got by using the ideal gas equation, you can see that there's about an error of about 2.1% when you use the ideal gas equation with respect to this approach. You compare with this approach. Then you also want to know the density, which will be right, and this will turn out to be 32.44 kilograms per cubic meter. And again, if you compare this result with the result that we obtained at the beginning of the exercise using just the ideal gas equation, you will see also that there's a 2.1% error when you use the ideal gas equation approach. And finally, for the volumetric flow rate at the outlet of the pipe, this will be, you have to use this factor over here, and this ends up being 0.05472 cubic meter per second, which when you compare with the answer that we obtained at the beginning by using the ideal gas equation, you will get a 3.6% error in the answer. So that's it. That's the end of this problem.